Hello, today we are going to be looking at L'Hopital's rule, which is a handy little tool when evaluating limits. So if you're familiar with limits, a couple of these examples you might already know how to do. So our first one here is limit as x approaches 3 of square root of x plus 2. This one's pretty straightforward. All we have to do is, got my pen here, plug in x equals 3, and that gives us square root of 3 plus 2, which is equal to the square root of 5. No trouble there. That was pretty straightforward. We're good to go. This one, however, as x approaches 2 of x squared minus 4 over x minus 2, you'll notice if we plug in x equals 2, then we get 4 minus 4 over 2 minus 2, which is equal to 0, over 0, which is not great. We don't want that. However, if we look at the numerator of this function, we can see that that is a difference of squares. And I can rewrite that as x plus 2 times x minus 2. My numerator and denominator, well, we have a factor there that can cancel out. And then we can just do plug in our x equals 2, which is 2 plus 2, and that equals 4. So we did get 0 divided by 0, which is not great, but we were able to avert that. Let's look at this next example here, which is limit as x approaches 0 of sine of x over x. Okay, so sine of 0 is equal to 0, and x equals 0. Well, of course, that's just 0. Bit of a problem here. We have 0 divided by 0. And unlike the first question, there's not really much we can do about it. There's nothing we can factor out, nothing that cancels, no other forms of sine of x or just x that we can use. So we have a bit of an issue here, having 0 divided by 0. And that's where L'Hopital's rule comes in handy. So L'Hopital's rule tells us that if a limit as x approaches a is equal to 0 over 0 or infinity over infinity, which is indeterminate, then we can instead take the limit x approaches a, instead of doing our regular limit, which would be f of x divided by g of x, we can instead do the limit as x approaches a, the derivative of f of x over the derivative of g of x. Okay, so I should rewrite this here, actually. Put my functions in there. So if you have the limit of f of x over g of x equals 0 over 0 or infinity over infinity, you can just take the derivative of the numerator and the derivative of the denominator, and then once again try plugging in that x equals a. Okay, so this is, and I guess I kind of wrote this out sort of funny, so I'll just get rid of this here. There. Bring this over here. This is what you would do instead. So we'll give that a go with our sine of x over x example. So as we tried plugging in x approaches 0, sine of x over x, we got 0 over 0. Let's try applying L'Hopital's rule and doing the derivative of the numerator and the derivative of the denominator and see what we get. So do this in a different color here. The derivative of sine is equal to cos. So now we're going to do limit as x approaches 0, cos of x, and the derivative of x is equal to 1. And so when I plug in x equals 0 here, I get 1 over 1, which is equal to 1. Crisis averted, we no longer have 0 divided by 0. So that's L'Hopital's rule in action. Let's look at another example of this for practice. So the limit as x approaches 0 of 1 minus cos x over x squared. So first thing we're going to do, because it could just be straightforward, we could just plug in x equals 0. If I do that, I get 1 minus 1 over 0 squared, 0 over 0. Not great. So let's apply our L'Hopital's rule, which says we'll do the derivative of the numerator and the derivative of the denominator and try taking the limit again. So in that case, let me try. I'll do a different color again. Yeah. So we're going to do the limit as x approaches 0. The derivative of cos is negative sign, so we're going to get negative sign, which is just going to be sine x over the derivative of x squared is 2x, right? And so now we're going to try plugging in our 0 again. In this case, sine of 0 is equal to 0. So we get 0 divided by 2 times 0, which is 0. Once again, we have 0 divided by 0. Not great, still didn't work out. However, with L'Hopital's rule, we can apply it more than once if we need to. So we've tried doing it once, didn't work. We can try it again and see if we get somewhere there. So you can apply L'Hopital's rule as many times as needed until you no longer get that indeterminate value. So let's try one more time and see where we go. X approaches 0. The derivative of sine is cos, so I'm going to have cos of x. The derivative of 2x is equal to 2, and that's equal to 1/2. And there you go. There's our limit. If you want to try convincing yourself of this to make it make sense visually, you can try graphing it. Now, I'll do a really quick sketch of the graphs here. It won't be perfect, so I definitely recommend putting this in Desmos or your graphing calculator. You can actually see what it looks like perfectly. So if you were to graph, I'm going to use orange for 1 minus cos x over x squared. It looks something like this. Again, this is not going to be perfect. Let me move it over a little bit. It should be peaking right there. And this point on the y-axis right here, that is equal to y equals 1/2. Okay. And then if I graph cos of x divided by 2, oh, where'd I go? Okay, there we go. We'll cut that out. If I graph cos x over 2, then I get something that looks like this. And I should use a different color. So I'll use dark green. So this is cos x divided by 2. Again, my graphing skills by hand are not great. But there we go. You get something like that. And if you put this in your graphing calculator, you'll notice that their limits both reach 1/2 as x approaches 0 from both sides. So when you're practicing L'Hopital's rule, if you ever feel like it doesn't make sense or if you start questioning what you're doing, you can always try graphing it just to take a look at what the functions actually look like and how it does indeed work when you're taking the derivative of the numerator and the denominator. Now we'll do one more example. In this case, we will look at what happens if you get infinity over infinity. So it'll be the same rule, but just a little bit different. So in this case, we're going to look at the limit as x approaches infinity of e, which is Euler's number, to the 2x over x squared. So if we plug in x equals infinity here, we get infinity over infinity. Not great. This is where we want to try using our L'Hopital's rule. So the derivative of e to the 2x is going to be 2e to the 2x, and the derivative of x squared is going to be 2x. So once again, we're applying that derivative of numerator over derivative of denominator. If I plug in my infinity here, I still get infinity over infinity. Not determinate, so that's not good. So we'll apply L'Hopital's rule again, just like we did before. So as you can see, it is quite common to need to do it more than once. So if I try it one more time here, as x approaches infinity, the derivative of 2e to the 2x is 4e to the 2x divided by the derivative of 2x is just 2. So in this case, I get infinity divided by 2, which means that my limit as x approaches infinity of e to the 2x over x squared is equal to infinity, that is an answer. It's not indeterminate because we're not dividing by infinity as well. So these are a couple examples of using L'Hopital's rule. And in summary, you'll want to use L'Hopital's rule when your limit gives you 0 divided by 0 or infinity over infinity, and you can't do something such as factor and cancel out. If you need to try something else in order to find the limit, you do the derivative of the numerator divided by the derivative of the denominator and take the same limit that you had in the first place. So hopefully that helps. This is a handy little thing to use when you're evaluating limits, and best of luck with your practice.